Okay, everybody. Last couple of topics here in nuclear, and we just want to take a quick look at how you get this energy and where this energy comes from in a nuclear change. And what scientists again eventually found out is that the energy changes within the nucleus are much greater than the energy changes that would take place in a regular chemical reaction when you talk about a change in bonding. So we just want to take a quick look at that. Just a little information here, just to give you an idea of the scope of the possibilities of the energy and what we can do with it. All right, so protons and neutrons. Basically, we got to look at the nucleus a little bit closer, and what we find out is that in the nucleus itself, at this point in time, uh, protons and neutrons are actually held together in the nucleus by a special force, and this force is not the positive negative force. Okay, this is called the nuclear strong force. So the positive negative force is different. Now, this force, which is a special force, only takes place in a nucleus. Okay, and it's the strongest one in nature, and it acts over only very short distances, and that's going to be key. So if you had a helium nucleus, you can see that this proton and this neutron, or this proton and this proton, and even the neutron behind it, okay, would be touching. They would have this very extremely strong force here that attracts them. The nature of this force, not really too sure about it. There's a lot of study going on with how this force arises, but we do know it's there. Okay, very strong. Now, as the nucleus gets bigger, the particles would then be further away. So just understand that the electrostatic force, okay, is the name of the plus and minus force that we all know and love that takes place between protons and electrons. Okay, so the electrostatic force is stronger, okay, when the particles here are further apart. So again, short distances. So if you have a very large nucleus, a nucleus that's very big, okay, like this, if this was a proton and this was a proton, you would have a strong nuclear force here. But the strong nuclear force would be weak. The electrostatic force would be strong, and these guys would repel. So protons that are close to each other will attract, but when they're far apart from each other, okay, then the electrostatic force is strong, and this force is weak, and that means the nucleus can break apart. Okay, so you have to understand what the balance of forces is. Okay, not a big deal. You're not going to get many questions about this, but you want to understand what's going on because it's going to help you with the next part. Okay, so we bring up the idea of binding energy. Binding energy binding means to hold together. Okay, and when we talk about bonds or chemical bonds, we talk about bond energy. So it's very analogous to that. And simply the binding energy is how much force you have to put in to separate the particles. So if I want to go into if I want to go in here and I want to separate this into separate particles, okay, I'm going to have to break that strong force. Okay, so I'm going to have to put a lot of energy into that. So it completely separates protons and neutrons. Okay, and so the higher they're bound together, of course, the more stable the nucleus is. So certain nuclei in the periodic table have strong nuclei, and some have fairly weaker ones. Okay, so this binding energy, just like heat and energy, is also released when you combine individual protons and neutrons into a single nucleus. All right, so when we take these guys and we mash them all together into that nucleus, you're going to get an energy release, right? Remember, when you put things together, in bonding, when we have bonds formed, we know energy is released. Well, if you form a nucleus, again, you release energy. Now, the energy that's released is way more than it is in regular chemistry, because you're forming such a strong attraction and such a strong bond, you get a large energy increase. Well, how big is it? And we'll give you a little idea. Now, the key to all of this, and what scientists have found, is that the energy that is lost comes from a little bit of mass that's lost when the nuclear particles combine. And in this sentence is really the core of what's going on here. Okay, scientists have found that when a nuclear particle is made, or a nucleus is made, it actually gets slightly lighter, and some of that mass is actually converted to some energy. So very little mass makes a lot of energy. Okay, Einstein kind of stumbled on this idea. okay, and ended up with his famous equation, which we'll see in a minute. Okay, so if you look at this slide here, what we'll see is a picture of just a couple of things I want to look at in this thing. So what we have is this um, four particles. We have a proton, its mass being about an AMU. Again, this little symbol is AMU, and again, protons have this much AMU. If you notice that neutrons are slightly heavier from the AMU. So we have four separate particles, each with its own mass. So think of these as four circles or four balls or whatever with separate masses. And if we add all these masses together, okay, we would get a total mass of 4.0302 before you add them, before you mush them together. So now we're going to take these particles, we're going to mush them together into a helium nucleus. So this would be a helium nucleus now, a new helium nucleus with a 4-2. Okay? So four particles. So what we find is the mass before was 4.0320. The mass after is 4.0015. So you can see this is lighter. Okay? Now, from the diagram, you're looking at this thing going, well, wait a second, why would it be lighter? What are we missing? What we find is that this is the missing mass. And what this missing mass does is this is converted to energy, and energy is released. Okay, a lot of energy. Okay, now how do you get this? Like, what is actually happening here? Okay, so we'll take a look. All right, so when combined, resulting nuclei weigh less than the individual particles that they came from. Okay, and this becomes the major announcement. The major announcement is here, and they've done experiments on this, that a small amount of mass is converted to energy, according to Einstein. Okay. And again, this is called, and I may have missed it on the other slide, this is called mass defect. Okay, actually two words. Let's call it mass defect. I think that was supposed to be on the other slide. That's a little bit of a mistake, I think, at the bottom. So let me just, yeah, right. No, it's okay. Right. So it's mass defect. We're all good. So a mass defect is defecting. So a little mass loss. You can think of this as defect. All right. So again, so what we do is this is part of Einstein's famous equation. We know E equals mc squared. Now, what does the E mean? E is energy. Okay. So this is your energy here. Okay. And what Einstein believed was that energy is going to be equal to mass. Okay. And this is called the speed of light. So the speed of light is actually a huge number, right? It's 3 and 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so you're talking about a huge speed of light, right? So if you take that and you multiply it by the mass, that's how much energy in joules you would get. So again, you need very little mass to create a whole ton of energy. And that really makes sense because right now, with regular fuels, like gasoline and oil, we need a lot of fuel to make a lot of energy. In this case, we need a very little fuel to make a lot of energy if, in fact, you're using nuclear fuel, if you're creating new nuclei. Okay, so some crazy facts here. Okay, so think about this. If you took 227 grams of coal and you put that in a barbecue, and you barbecued something over coals, or you were going to create electricity, you would burn that coal. Okay, again, a chemical reaction would be combustion, right? You would burn that in a combustion reaction, which is really a chemical reaction, and you would get about 20,000 joules. Okay, however, if you burned the same gram amount, so the same weight of uranium, okay, which is roughly a mole of uranium, right? So 1 mole. Okay, the gram folium mass of uranium is 235. So that would be 1 mole. So I wanted to get it close to the amount of coal that you had. So gram for gram here, if you compare them, basically, you would create this amount of joules. Okay, so think about the amount of difference in amount of energy you would use for a given mass, okay, of that nuclear fuel in nuclear reaction. So the attractiveness of this to be used in a reactor really helps. So again, what do you really want to know about this? What you really want to know is that the nucleus is held together by this really strong force, okay? And to break these forces and create new nuclei involve large amounts of energy and according to missing mass. So mass is definitely converted to energy, and this is definitely what you're going to want to know this for your test. You're definitely going to want to know this information. This is definitely will be asked, and you definitely want to know that the nuclei weigh less than before because this mass is converted to energy, so it's going to lose mass. Okay, so that's it on that. The next step is looking at something called half-life. I decided to put this in one video, so at least you'll have everything together. And we look at half-life. We look at the time it takes for something to decay. We really didn't look at that before. Okay, so really, what is half-life? Half-life is simply the time it takes for half of a radioisotope of a sample to decay to some other element. Okay. Now, again, half-lives can be long. They can be short. They can be anywhere from milliseconds. They can be fractions of seconds, and again, they can also be millions of years or billions of years, depending on that type of nucleus. So it really depends on what kind of nucleus you're dealing with. All right. No humans can affect the half-life. So if a half-life is 30 years for half a sample to decay, then you can't do anything about that half-life time. Okay. So, for example, you can't change the temperature and pressure of something and affect its half-life. All right. It's the average decay. Basically, this is an average time of all the nuclei in a sample. Okay. So just to give you a little pictorial version of this, is let's just say you have a radioisotope, and again, this is unstable. All right, and this is the stable version. So we'll do something real simple. So let's just say you started with a sample of this pure radioisotope that's unstable. Well, after one half-life, so we're starting with 16 little atoms here. So again, and this is not exactly accurate, but it gives you an idea of what you're thinking. All right, and let's just say so after one half-life. Okay, so this would be a half-life. Okay, and let's just say it's 1 year. I'm just gonna make it. Well, let's just say it's 1 day. Let's use 1 day. So let's just say this is 1 day. After 1 day, which would be a half-life, we would have roughly half of these guys would then decay to some new isotope. So after one half-life, you would cut it in half to 8. After another half-life, over another day, you would cut that from 8 until 4. So notice that I'm cutting this in half after 2 half-lives. And let's just say I continue and I go after another day, I ended up with 2. Okay, and I would keep doing this. And notice that each time I do this, I'm cutting the yellows in half, right? And I'm going up in my new atom. And eventually, you'll convert the yellow guys into all the pink guys, okay, as you mount these half-lives. Now, the time it took to go from this all the way over to this version would be the addition of all the half-lives. So that would be 3 days, okay, of taking half, right? So that's the way you want to kind of look at this. So that's the way you can visualize or think about how half-lives work. Again, we can do this by mass, typically do it by mass, but this is a good visual way to see it. All right, so how do you actually answer these problems? And these problems can be a little tricky, but there's a plan. So I'm going to show you the plan. So we're going to organize it like this. The way I want you to organize this, okay, is use a simple chart, a little simple table. Now, again, if you were in other classes, your earth science teacher might have done this differently with a chart. Different teachers use different things. I have found that this is the best method to do this with. So I would like you to do this. Make a chart. Make a little picture of this. So basically, you're going to be given a starting mass, okay, or some starting fraction, or percentage, okay? So a fraction or percentage you're going to be given, some starting point, okay? And then you're going to have some type of ending point. Ending mass, okay, this could be a percent, this can be a fraction. All right. All right, so again, it's an ending mass. Again, I'll put these in parentheses, ending mass or fraction, okay? And then there's going to be a total time that's going to be able to get there to some ending mass or fraction. And again, this doesn't have to be going down to 0. This can be at some point, okay, you're going to be going there. And what you're going to do is, the way you get there is by taking successive half-lives. So this is going to be the half-life value, okay, or the half-life time, okay? Now this half-life time is going to be constant. So basically you're going to make a loop is going to be a half-life time. So you can think of this as a loop. So your half-time loop, okay? So you take half of that, half of it again, half of it again, and you keep going. I'm just going to put 5 here just because I can fit it. All right. So again, let's just say you started with 100% of your sample. I'm going to make it 100%. Well, after a half-life, you would have 50% left. After another half-life, you would have 25% left. Now, the half-lives are going to be constant. So each time you have a half-life, each half-life is a set amount of time. Just like a day, when a day goes by, then you start a day again, and then you start a day again. Okay, so then you would have 12.5 here. Okay, half of 12.5 is 6.25, and then half of 6.25 is 3.125. All right, so again, you could see how this kind of works. You're taking half each time. Now, on the points go your masses. In the valley here, that's your loop, that's your value of your time. Okay, now each problem is going to give you, okay, 3 out of these 4 values. Okay, so you have 1, you have 2, you have 3, and you have 4. So every problem will have to give you 3 out of these 4. So they could give you 1, 4, and 3, and you'll ask them to find 2. They can give you 2, 3, and 4, and ask you to find 1. The language can be tricky. You just have to work through it and see what you have, and then see what you can do to get your loops and so on. Now, if you're going that way, you're going to take half. If you go this way from the ending mass, you're going to times 2. Okay, and above all, you're going to see table n for half-life times if needed. Okay, so that's important. So if you need it. Okay, sorry about the bad handwriting, but needed. Okay, so half-life. So the value of a loop might be on table n if you need to find it. Again, you're going to do this by practice. So let's just look at a quick example of how we can do this. It says how much of a 10-gram sample of cobalt-60 remains after 15.81 years. So you have to think about this. So after that amount of years, that's going to be my total time. Okay, so I already have my umbrella. I have my total time is 15.81 years to go from one point to the other. So that's my umbrella. Okay, and it says how much of a 10-gram sample. So basically, I don't know how much is left, but I know I'm starting with 10. Okay, I have a 10-gram sample of cobalt-60. Now, it appears in this problem that I only have 2 of the numbers, right? Because they gave me the total time, and they gave me the starting mass, and they're asking me for X. So I don't know that. I would have to know how to get there, but they're not giving me the half-life either. However, they did tell me it was cobalt-60. So I can go to cobalt-60, look it up on table N, okay? And in this thing, I find out that in the problem down here, 1 half-life, again, this is cobalt-60 here, 1 half-life is then 5.27 years. So I'm getting that from table N. So we know the value of 5.27 years is my value of 1 half-life. And what does that mean? That means after 5.27 years, I'm going to go take half of 10. Now, I got to eventually go to X somehow, all right? But it's telling me an important point. It's telling me that 15.81 years is the time. Now, if 5.27 years is a half-life, I could go another half-life still and go to 2.5 grams, right? And that would be another 5.27 years. Well, how much do I have to go? How many half-lives do I have to go to get to 15.81? Well, an easy way you could do that is simply take 15.81 divided by the timestamp of 15. And that is roughly going to be 3. So that's the number of loops I have to go, or the number of half-lives. So I go one more half-life. Okay, so I take half of 5, half of 2.5. Okay, and I go one more half-life. Okay, and that would be, give me 1.25 grams. So that is my answer. So important, right? So there is my 4 numbers that you would normally see in the chart above. Okay, so again, the number of half-lives added together equals the total time. So if you could cheat a little bit and say, okay, the total time, I know how many loops I'm going to go by doing this. All right, so I hope this helps. If you have to go back over, check it out. Use this every time it works. It will work every time for any problem that you do. You just have to practice. All right, so good luck. We'll see you soon.